Today we're going to be talking about generators and transformers, not the robots from the movies, but transformers that you might see on the electrical pole outside your house that they transform voltage, which is actually really cool. It's a weird loophole in the rules of the universe that let us transport energy very efficiently from one spot to another, and it just by happenstance that the way we make the energy lets us do this thing that lets us transport the energy from point A to point B in much more efficient ways than it used to be. When the great debate between Edison and Westinghouse and Tesla about whether we should use AC or DC in our electricity generation in the United States, alternating current or direct current. When we were using direct current, you had to have generators really nearby. You couldn't transport that energy through lines very easily because the current would be very large, and the energy lost to the environment through heat, the wires would heat up, and we'd lose most of the energy by the time we would transport it very far at all. So, as it turns out, because we chose AC, or AC won out in that battle, we're able to transport electrical power much larger distances than we could otherwise through the use of transformers, which transform the voltage from relatively low voltage to relatively high voltage with much less current. But we'll talk about that later. Before we get into that, we're going to do a little bit of review. The first thing we talked about in this chapter was magnetic flux. Magnetic flux is how much magnetic field is passing through a given surface area. The surface area could be any shape. We mostly have been doing loops of wire because that's pretty common. But it could be a square like in this picture, or really any shape at all. The flux, the magnetic flux, represented by the Greek letter phi, is equal to the B field, so the magnetic field vector passing through, the area of the surface that it's passing through, times the cosine of the angle between those two. The area vector, this is a little confusing for some folks. If you imagine a piece of paper on your desk, you would say that piece of paper is facing up, even though the paper is flat. It's not up, it's horizontal. But the face of that paper is pointing up. Same thing with a surface area vector. This might be flat on your desk, but the area vector is pointing straight up. So that theta is the angle between the B field vector and the area vector that's, we say, normal to the surface, or perpendicular to the surface, pointing in the direction the surface is facing. Flux, people forget this as well, so if I ever ask you to calculate flux, like on the exam, you'll include the unit Webers. WB is the unit for flux. It's measured in Webers, which is 1 Tesla times meters squared. Tesla being the unit for B field, meter squared being the unit for area. Why do we care about flux? Because we use flux to calculate the induced electrical voltage, the induced EMF. The equation for the voltage induced, EMF is just a fancy word for voltage, and the equation for that, N, is the number of coils. In our example, there was just the one surface, so there would just be one coil. If it's a single loop, N is 1. If you have a bunch of loops, then N is however many loops you've got. Delta phi is your change in flux. Delta T is the time that it takes for that change in flux to happen. Change in flux can be a change in anything that goes into flux. So you could change the B field, that's part of the flux equation. You could change the area, or you could change the angle between them. Changing the angle is the thing we're going to be focused on today. That's what generators usually do in generating electrical power. So that's going to be our focus for the majority of this video. But I do want to do at least one example. I mentioned it last class, but I didn't actually get a chance to do it. So I want to show you this example for how that works. We we have done an example in class where we had a delta phi due to a changing magnetic field. We were moving the magnet. You could also change the area, and this example has us doing that. And then later, when we talk about generators, we'll be changing the angle. So any of those three components can change and give us a delta flux, a change in flux. In this case, we have a loop that is all conductive. There's a resistor in that loop and 3 metal rails. This crossbar is able to slide, and it is moving with a velocity v to the right. We're given the distance between the bars and the velocity that it's moving at. And we're asked to calculate the resultant EMF that's produced by increasing the area through which this magnetic field is acting. So by increasing the area, by moving this bar to the right, we're increasing the area of our loop. And by increasing the area, we're also increasing the flux into the screen. Notice the B field is pointing into the screen. All of those little X's mean it's pointing away from us, going directly into the screen. So we are increasing the flux into the screen, which means we're going to induce a current that makes a B field out of the screen. Last class, we spent a substantial amount of time going over this example right here, Lenz's law. I did want to show you, as we're getting ready to do this problem, there's sort of a problem-solving strategy, an order of the process that you're going to go through. A lot of people were asking questions like, well, does that mean that every time the north side is facing, then it should be clockwise, and every time the south side is facing? You can't do that. You can't generalize like that. What you can do is understand what's happening, look at the situation, and determine the direction of the current that would give you the proper answer. So, step one for solving any Lenz's law type problem. Anytime we're trying to figure out the induced current, step one, draw a picture. I don't know why college physics students are so hesitant to do this. Always draw a picture. It helps. It helps you to organize your thoughts and visualize what's actually happening. Step two, determine the direction of the B field, the magnetic field that is causing the induced EMF. So if I'm moving a magnet, or if I'm changing the area, it doesn't matter. I have a B field. That B field has a direction because it's a vector. Determine that direction and include that in your drawing. Next, determine whether the flux is increasing or decreasing. I told you yesterday, or last class, that you can just plug in numbers. So you know it's going from like maybe a strong positive to a weak positive. Put in numbers. Put in a large positive number and a small positive number. Do final minus initial and see if the flux is increasing or decreasing. Once you know whether the flux is increasing or decreasing, you can determine the direction of the induced B field. So you have a B field, you have a magnetic field that is causing the change in flux. That is part of that change in flux. It's causing the induction of the EMF. You will get a resultant B field because of that EMF. It's going to be in the opposite direction. It opposes the change. So if my change is into the screen, then the induced B field is out of the screen. If the change is out of the screen, then my induced B field is going to be into the screen. After that, you just use your right-hand rule to determine the direction of the current needed to make that B field in the direction that you just found. No shortcuts. A lot of people kept asking questions because they wanted a shortcut yesterday, last class, not yesterday, a couple days ago. But you can't do it. You got to go through these steps. Go through them every time or you're going to get mixed up. But if you know these steps, none of these steps are particularly difficult. You can do it. I have faith in you. I know you can do it. In fact, let's do it right now. Let's find out what's going on. So I have a drawing. I don't need to draw it anymore. I have a B field that's going into the screen. If I'm increasing the area, my flux is increasing. Since the B field is going into the screen, the flux is increasing. It's increasing into the screen. My change in flux is into the screen. So my induced B field has to come out of the screen. How would I get an induced B field inside of this loop that's coming out of the screen? Use your right-hand rule, and you should find a counterclockwise current will give you an induced B field out of the screen. All right, we know the direction of the current now. If you want more practice with this, there's a bunch of problems on the homework that make you do this. There's also problems in your textbook. You can always email me. We can set up a Zoom meeting between now and Monday. We can go through some practice if you want to. There's only a finite number of ways that it could possibly go. So jumping back here for a second, either you're increasing it, in this case, if we're on the up and down movement of the magnet, you're increasing it up, you're decreasing it up, you're increasing it down, you're decreasing it down, or there's no change at all. There's really only that many possibilities. You can reorient it so it's into and out of the screen or left and right. You can change the orientation of the loop, but regardless of the orientation of the loop, really these are the only possible combinations. Back to the problem at hand. So we're given some information. In this particular case, we are given that the length of the rod, so this length, L, labeled on the drawing is 1 meter. The velocity of the moving bar is 3 meters per second. And the strength of the magnetic field is that of Earth's magnetic field, 5 times 10 to the negative 5th Tesla. So we're going to find the change in flux, and we're going to use that to find the induced EMF. So we determine the direction of the current using Lenz's law. We know the current is going counterclockwise because the change in flux is going into the screen, and therefore the induced B field has got to come out of the screen, which means we have to have a counterclockwise current to give us that B field in the middle of the loop coming towards us. Now let's figure out how much EMF is actually generated, how much is induced. EMF equals N delta phi over delta T. N is 1 because there's only one loop. If we had more than one loop, we'd have to include an N value. Don't forget it. There's a homework problem that I messed up because I forgot to include the number of coils. Make sure that's in there. But in this case, it's just a 1, so it drops out. Delta phi is going to equal, well, the B field is uniform. It's not changing. So there's no delta B to deal with here. What's changing is the area. And theta's not changing, and theta is 0 degrees because the area vector is going into the screen and the B vector is going into the screen. So cosine theta is just 1. So delta phi is going to equal B times delta A. But what is delta A? What is the change in area? Well, it was where that dotted line is, and it now is here as it's moving. So the change in area is this part that I'm shading in. And that is a rectangle, and we can calculate the area of that rectangle by multiplying the length times the width. The length is a given value. The length of the rod, which is given in the problem. The width is delta x. We don't know delta x, but we could find it because we know the velocity. So for the time being, I'm going to write delta phi equals B times delta A, but delta A is length times width, so it's delta x times L. So we don't know delta x, but we're going to keep it there for now because when I put these equations together, there's a cool little trick that we can do, and hopefully you see it. So EMF equals delta phi over delta t, but delta phi is this stuff. So EMF is going to equal that stuff, which is B times L times delta x, all that divided by delta t. Well, so it's all of that divided by delta t, but I can divide, because of how algebra works, I can divide just that last part, that delta t, into the delta x, and that is our velocity. So the EMF is going to equal B times L times V. And all of that's given in the problem. All of that is given information. We can find the induced voltage. Now, once we have that voltage, whatever it might be, you can calculate, you can plug the numbers in if you'd like. Once we have that, if we know the resistance of our resistor, we can calculate the current, because V equals I times R. So I would equal the induced voltage that you just are calculating divided by R for that resistance, the resistance of the resistor in the circuit. With the magnetic mysteries, so hopefully you have done some research on what's happening. I'll give you a little clue if you haven't. Eddy currents and magnetic damping. Damping is something we're going to talk about later in our oscillatory motion chapter. So this is a little bit of foreshadowing, but these slides actually will help foreshadow those concepts. They tell us sort of how they work, at least in terms of magnetism. Damping just means pulling energy out of an oscillating system, so it eventually comes to rest. The fans that were swinging into a magnetic field in between those strong magnets, they were not magnetic themselves, but they were conductors, and when they swing into the field, the magnetic field that's affecting them changes, so the area being affected changes, so there's a change in flux, and when there's a change in flux, we get an EMF. And while it's not a loop of wires, it's still a surface area, and it still has electrons that are caused to move with that induced EMF. So we get what's called eddy currents, like eddies in a stream, those little whirlpools on the edge of a creek that you might be like playing in, whatever. Those eddy currents are moving charges. Moving charges make magnetic fields. Magnetic fields will feel the effects of the magnetic field it's moving into. And if you do your second right-hand rule, you'll see that the force on both ends of the swing. Now, before it gets into the field and while it's already in the field, there's no change. But as it's entering or exiting the field, in both cases there's a change in flux. And when there's a change in flux, there's an induced EMF. When there's an induced EMF, you get an induced current. This eddy current will induce a force that causes it to slow down. In both cases, you can do the right-hand rule and you can check this. The force is going to be, for the object swinging to the right, going to be to the left. I'll let you guys figure out why the slots in the fan made this effect substantially less, reduced by quite a bit. We use it in balances for measuring masses because these are really sensitive and any force will cause them to start to oscillate. So we need something to make that stop, and we use magnetic dampers to make that slow down, to reduce that. We also use it in separating metals from non-metals in recycling plants. So that's kind of cool. We also use magnetic induction in metal detectors. That's why you have to walk through a ring. And lastly, last example for you, we use it for braking in roller coasters and trains. So all of those are pretty cool applications of the concepts that were demonstrated in those 3 demos that I showed you on Wednesday. All right, on to the new stuff. The actual topic for today, changing theta. I told you you can have a delta phi, a change in flux, by changing B field, like in my little flashlight I showed you, by changing area, like the problem we just did, but also by changing the angle. If I have a coil of wire that's attached to a handle like this, and I rotate that handle to various angles, in this case, it's rotated so that the area vector is perpendicular to the B field vector, and there will be no flux. There is no magnetic field passing through the wire. If I turn it 90 degrees so that it is in the faded out position, now there's a maximum amount of flux. The area vector and the B field vector going the same direction, so I maximize the amount of coil that's facing the magnetic field. So I get the most magnetic field going through it. I have gone from zero flux to a maximum amount of flux, whatever B times A is. If I continue to spin it, the flux will continue to change. This is how our electric generators work. We, instead of having a hand crank like this, we have a turbine like this. Here's a picture of Joey when he was really little, sitting next to a turbine that was used in the hydroelectric plant at Niagara Falls. It's huge. This one, not so huge, but it spins really fast. So we can transfer mechanical energy into electrical energy by spinning turbines and rotating either a set of coils or a set of magnets, either one. We're either rotating the coil in a magnetic field or we're rotating a magnet that is surrounded by coils, so the angle is constantly changing. By doing that, we can induce an EMF and generate electrical power. But notice that if I continue the rotation, if it keeps spinning, the angle is going to go from 90 to 0 to 180. It's going to continue around so that it's going one way, and then it's going the other way, then it's going the one way again, then it's going the other way again, causing the current that is induced to continually flip, to change direction, to alternate between positive directions and negative directions. So when we spin a turbine to generate electrical energy, by the very nature of how we make it, we create an alternating current that's switching between positive and negative. The energy we generate in the United States is generated in an oscillatory manner like this, so that it's alternating at a frequency of 60 hertz. So if you hear a hum in the electric boxes on electric poles outside your house, that hum is at exactly 60 hertz. 60 times per second it oscillates, which I think is kind of neat. We can calculate how much it oscillates, or how much energy we get out of that oscillation, using a generator equation. Now, I went too far ahead. The change in flux that we are going to obtain from this depends on how fast it's oscillating, how fast you're spinning that handle. So flux equals NBA cosine omega t. Let's break that generator equation down. N is the number of loops. In this picture, there's only one loop, but in reality, we use solenoids. We use sets of loops. So N would be the number of coils in that set of loops. B is the strength of the field, so how strong are the magnets that you're using. A is the area of the loops or the coils. Cosine is just a cosine term. Omega times t is actually the angle, but since the angle is changing, we use omega, which is the rotational velocity. It's the radians per second, or the RPMs of the rotation of our coils, and t is however much time has gone by. Since EMF is the rate of change of phi, it's delta phi over delta t, we can actually, if you were in a calculus-based class, I'd show you that this is the derivative of the flux equation. So the EMF is just the derivative of the flux equation, and that's where this comes from. You don't have to know how to do that. In fact, you don't even really need to know that that's where it comes from, but now you do. So you're stuck with that forever. You'll remember. So it does come from a derivative. You don't really need to know that. What you do need to know is this is the equation. At any given moment, the induced EMF will be omega, which is the rate of rotation, times n, which is the number of coils, times b, which is the strength of the field, times a, which is the area, times the sine of omega t, which is the rotational velocity, times time. The maximum EMF, and this is one you have to use for your homework. This is probably what I would ask for, because it peaks and it goes from positive to negative to negative. The highest that can be is when the sine term is 1, because the biggest the sine term can be is 1, or negative 1. So since the maximum is when this term is at either 1 or negative 1, the maximum EMF you can generate, the maximum voltage you get, is just that first part of the equation. So EMF naught is the maximum EMF. It equals omega NBA. Omega being the rate of rotation, N being the number of coils, B being the magnetic field, and A being the area of the coils. So we will do at least one homework problem where you use this, where it's asking you to calculate the maximum output voltage for a generator. This is the equation you're going to use. How do you increase the maximum EMF you get? Well, you increase any one of those terms. You can add more coils, you can have a stronger magnet, you can have bigger coils that are spinning, or you can spin them faster. In essence, like I said, we're just transforming mechanical energy into electrical potential energy in the form of voltage. Fun fact, electric motors are the exact same thing, but in reverse. It's using the opposite process to transfer electrical potential energy into mechanical energy. So if you're ever in need of an electric generator, this is a true story. You can take a small electric motor and spin it backwards. If you spin it the opposite direction that it wants to go, you'll be turning your mechanical energy into voltage. So if you if you take an electric motor and you pull it off of the battery that it's attached to, and you hook it up to a voltmeter and you spin it backwards, that voltmeter will read the voltage that you're generating. So if you hooked it up to like a windmill, that little motor would become an electric generator. So if you find yourself in a zombie apocalypse and you need to generate some power, that's how you're going to do it. So how do we normally do it? Well, in our power plants, we have some heat source, like burning coal or burning some sort of fuel, nuclear energy, whatever it might be. We have some way of generating heat that we use to boil water. When we boil that water, it makes steam. And when you make steam, the steam takes up more space than the water that it used to be, which means we are increasing the pressure in the container. When we release the steam, that high pressure steam wants to escape, and it escapes really quickly. If you think back to the unit on pressure from Physics 1, the high pressure fluid wants to move to the low pressure area. We give it somewhere to go, it's going to go there really fast. When we give this high pressure steam somewhere to go, we make it go through our turbine, and it causes the turbine to spin. The turbine spins, it moves our magnets or our coils, causing a change in flux, which generates electrical power. I showed you the picture. These are what the turbines look like. This is from a steam generating power plant. This is from a hydroelectric plant in Niagara Falls. All right, let's change gears. Let's transform to our next topic, transformers. I actually used to have a transformer that looked exactly like this from my first trip abroad way back in 2005, which is early in the life of most of you. Let's see. So what is this thing? Well, if you travel to another country, the power that they generate is at a different voltage level. So if you plug your electronics into those outlets and they're not made for that voltage, if they can't handle that voltage, they might catch on fire, which is not really great for your travel plans. So this thing, this box here, transforms the voltage from whatever it is to whatever it's supposed to be. In our case, we want 120 volts. That's what we want our electronics to run off of. That's when we plug them in the wall here in the United States, what they are getting. If you go to some countries, they have 220 or 240 or some other voltage that isn't what our electronics are made for, so we need to change it to what it is made for. So we use a transformer. When we transport energy from the power plant to our house, it is much more efficient to do this at a very high voltage because power equals I times V, current times voltage. If we have a high current going through the slightly resistive wires, the power loss is I squared times R. Power loss in the line equals the current squared times the resistance of the line. And even if the line has low resistance, if the current is high, that current is squared, and we get a really large power loss. If we have a large power loss to heat in the environment, then not as much power is getting to our house from the plant. And if we go too far, remember that the longer the wire, the more resistance. Then if you're going long distances, the resistance goes up and the power loss goes up too, and none of the power gets to our house. So that's no good. So instead, we convert using a transformer from relatively, it's still high, but it's relatively low voltage, 12,000 volts at the power plant, to really high voltage, like 400,000 volts, which is going to be really low current. The relatively low current will have less loss of energy to the environment. I squared times R, the power loss, will be reduced. Now, we can't have that high of voltage when it gets to our house or it will blow up all of our electronics. So we have what's called so on this end, we are stepping up to high voltage, but on the house end, when it's coming to our house, we have a step down transformer that's going to reduce the voltage from this really high voltage to a lower voltage. And then we have another step down transformer down to 120 volts. It says 240, but ultimately when it gets to our outlet in our wall, it's 120. Okay, that's a lot of information. Let's talk about how it works. It's actually a pretty simple design. Do you remember I told you when we very first started this chapter that Faraday did an experiment and it didn't work? Well, that was kind of tongue-in-cheek. It kind of did work. It gave us a transformer. We have a set of coils on this side. The input side is called the primary side. That's why it has subscript P. So we have an input primary voltage and an input primary number of coils. When I have a voltage attached to a coil of wire like this, we're going to induce a magnetic field. Since it's an alternating current, that magnetic field is constantly changing direction. Up, down, up, down, up, down, up, down, 60 times per second. On the other side of this iron metallic square loop here that's becoming magnetized is another coil of wire. In that coil of wire, we have a constantly changing magnetic field. It's constantly changing direction, up, down, up, down, up, down, 60 times per second. Every time that changes, we have a change in flux in that coil of wires. And every time we change the flux, we induce a voltage. So we have an output or secondary number of coils and a secondary output voltage. Since the number of coils is different on both sides, even though the change in B field is going to be the same, since we have a different number of coils, we'll have a different output voltage. The secondary set will have a different voltage, either higher or lower, depending on whether I have more or less coils on the output side. This is super cool because we don't lose any energy in this process. Thermodynamics tells us we always lose energy, but the energy loss in this process is minuscule, it's tiny. So it's nearly perfect. So we can do this as many times as we want to, trading high voltage for high current or high current for high voltage without energy loss. The equations that you need to find out how much the exchange rate is come from the fact that power in equals power out. So the power on the primary side equals the power on the secondary side. So I times V on the primary side equals I times V on the secondary side. And from that, we can derive the following equations. Voltage secondary divided by voltage primary equals current primary divided by current secondary. If I know any three of those things, I can find the fourth thing. Similarly, current secondary divided by current primary equals the number of coils primary divided by the number of coils secondary. You don't have to memorize these, obviously, they're going to be on the equation sheet, but you do have to know what they mean. So if I have like in this case, a small number of coils on the primary side and a large number of coils on the secondary side, that would be N primary would be a small number, and secondary is a big number. And it'll tell us what our input current is, so we can calculate our output current. We can do the same thing for voltages with this equation up here. All right, that's the theory. Let's put it into practice with a few practice problems from your homework. Question 10 in the homework asks for the peak voltage from a generator. We're given how many turns, it's rotating, we're given the diameter, and we're given the RPMs, which is the rate of rotation. That's probably the trickiest part of this problem, is this rate of rotation. Something I did not mention yet, but is very important. I alluded to, didn't actually outright say, that we want the unit for our angular velocity to be radians per second. Right now it's revolutions per minute, so we're going to have to do a conversion. Otherwise, all of the information we need is pretty much given. The equation for peak voltage is EMF sub 0. It's going to equal omega n B A, where omega is the rate of rotation, n is the number of coils, B is the magnetic field, and A is the area. So we need to find each of those things. Number of coils, we know, given in the problem. The rate of rotation, omega, we're going to have to manipulate. So if omega equals 3,600 revolutions per minute, one revolution is equal to 2 pi radians, and 1 minute equals 60 seconds. We can multiply by 2 pi, divide by 60, and we'll get the rate of rotation, the angular velocity, omega, in radians per second, which is what we need. So then we'll have rate of rotation, rate of rotation. Here, we'll have the number of turns. Next, we need the B field. We got that. That's given. 0.85 teslas for mine. It'll be something different for yours. And the area, we don't have the area, but we do have a diameter. If the diameter is 0.1 meters, the radius will be half of that. So radius equals 0.05 meters. The area is going to equal pi times the radius squared. Then I will have all of my bits of my equation. I'll have my omega, my angular velocity in radians per second. I will have my n given in the problem, my b, the magnetic field, also given in the problem in Tesla, and my area in meters squared. Those are all the correct units. It will give me an output in volts. Plug them in, multiply them together. Number 11 is a transformer problem. We have a transformer used for rechargeable flashlight batteries. It is a 500 turn primary side. Primary is the input side. The secondary turn is 8. Secondary side is 8 turns, and the input or primary voltage is 114 volts. It says what is the output voltage? That would be the secondary voltage. So we have the N primary. We have the N secondary. and we have the V primary. We're asked to find the V secondary, the output voltage. Uh, the equations from the PowerPoint, we have V sub S over V sub P equals N sub S over N sub P. We're going to solve for V sub S, which is what we're trying to find, the output voltage. So multiply that V sub P up, we get Vs equals Ns Vp divided by Np, and we'll get our secondary or output voltage. The next part, B, is asking us to find what input current is required to get an output current of 4 amps. That would be the current on the secondary side, so I sub S. We have the same information as we had above, so we know the number of coils on both sides, and we know the secondary or output current, so we've got to figure out the input or the primary current. So if we know I sub S divided by I sub P equals N sub P divided by N sub S. This is right from your book or from the PowerPoint. We can solve that for I sub P and get our primary, our input current. Next, we're asked to find the power input, how much power is input. So we have to look at the input side, the primary side, and we can use any of our power equations, but since we know I and we know V, I would say the best one to use would be P equals I times V. So since it's the input or primary side power, we're going to use IP and VP. And we know both of those things. Multiply them, and you should get the input power. All right, finally, question number 12. A large power plant generates electricity at 12 kilovolts. An old transformer converted that to 330 kilovolts. Um, it's replaced with a new transformer that is 765 kilovolts. Um, higher voltage means lower current. Lower current means less line loss. So it's going to be more efficient for cross-country transmission. All right. The output power is 1,000 megawatts. Mega means 10 to the sixth. And the line resistance is also given. That's going to be important later on when we're calculating the actual power loss, which is what it's asking for. It says, what are the old and new power losses in the lines as it's transmitting the power? In order to find the power loss is going to equal I squared times R. So I'm going to need the output current uh, of the transformer for the old and the new. So we'll do the old first. And we know some stuff. We know V primary. That's given in the problem. For mine, it's 12,000 volts, 12 kilovolts. We know the output power. So we know the power on the primary side is equal to 1,000 megawatts. So from that, I can actually find the output, the primary side current. So I know the power, and I know P equals I times V. So I on the primary side is going to equal that power divided by V in the primary side. So that's going to give me IP. Once I have IP, I can use my transformer equation. So
IS. I'm going to solve it already. I'm not going to write the whole thing, so just to save space. IS equals IP times VP divided by VS. We have the secondary voltage, so the old one has a secondary voltage given in the problem. Mine's 330,000 volts. Yours will be something different, but you'll still use the same equation to find the output secondary current. Once we have the output current, we also know the resistance. We can use this equation down here to find the power loss in the line. So that would be for the old. For the new, we're given the same information. You just do it again, but for the new voltage. So you solve them both the same way. You just go through the process and compare the two, and it is a substantial difference. You lose quite a bit less with the more efficient, higher voltage transformer.
But the last thing I want to talk about is the exam Monday. We will be doing a review session Sunday evening when I get back to Erie, but in the meantime, I wanted to just go over the topics that we have done very briefly since the last exam. So, exam one was back in February, right in the middle of February. So, since then, we have talked about current and Ohm's law. We've talked about resistance and resistivity. So, what makes a resistor, and how much resistance it has based on the voltage and the current, but also on the physical parameters. Resistance equals rho times L over A. We also talked about electrical power. We talked a little bit about that today in this lesson, but that was introduced way back then. We talked about putting resistors in series and in parallel. We did do a bunch of problems and applications of Ohm's law. We didn't talk a lot about AC versus DC back then. We've talked about it more since then, but not really much at the time. So there's not much to say there. EMF is just a fancy word for voltage, but we did spend a lot of time talking about voltmeters and ammeters. You've talked about them in class and in lab. So information about those, it makes really good multiple choice questions. Complex circuits, Kirchhoff's rules. Kirchhoff's rules were the kind of difficult bookkeeping with the multiple batteries, multiple currents, where you have to do the loop rule and the junction rule. So that is fair game. After that, we started talking about magnets, ferromagnets, electromagnets, inducing magnetic fields from moving charges. So magnetic fields on moving charges, they feel a force, and also from moving charges. Current carrying wires make magnetic fields. We did problems with each of those. We talked about induced EMF and magnetic flux. That was this week. That's Faraday's law also in generating electricity. And then today we talked about generators and transformers. The magnetic mysteries was Lenz's law, so I reversed the order of these because I wanted to do the demos in class. Eddy currents and Lenz's law was the direction of induced EMF. So those are the topics that we covered since last time. We will go through and work through them in detail during the review, but in the meantime, that's what you can look up, what you can study. We did problems, as I mentioned, in most of those, either in the homework or just in class. That should give you a sense of what's to come for Monday's exam. If you have questions, feel free to email, or we can talk during the review session on Sunday.